I don't want to stop this.
Okay, so actually I think now that we are more or less aware of my scenario and so on, I don't need to get trapped into the details, and I can just say like possible strategies I have considered to deal with this, and some things I've learned in the process, and you have some other ideas or experience, you can share it with me. I will be happy to hear. Okay. Try to do this, or try to convert this expression into a simpler expression somehow, so you can take advantage of algebraic operations and try to formulate your problem somehow else. So for example, in my case, I considered like if I have this sum of logarithms, I can say that I have the logarithm of the product, and then since this is a maximization problem, this is convex and monotonically increasing, I can get rid of the logarithm, so I can express this problem to be equivalent to the maximization of the product of the binary logarithm of this for each u. So this is, I would say, the first approach. Just try to formulate your problem somehow else, because maybe you think it's non-linear, but you can express it in a linear ways, and this actually happens frequently. Unfortunately, it doesn't always work. You know, maybe if I was like the logarithm of a polynomial, then it will have been better. But this is a logarithm of a logarithm of a rational, so it's not as nice. But this is like first thing I will suggest. Just try to convert algebraically your problem into something else. Maybe it's easier to solve. Second thing, of course, to try is to just plug it into a solver and let's see how it does. Because there are, as Arlet also has mentioned last week, there are some nonlinear solvers or integer programming solvers out of the box, and you can try them out. And this is something I will actually do. I haven't done it yet because I wanted to see how far I can get, like with theory first, and then I will try. And also the motivation I have to try to do this theoretically is because in the scenario I showed you before, the problem changes more or less every time the user positions change, and this is very frequent. So if my algorithm takes even 30 minutes to solve the problem, it's not valid for me. If this was a deployment problem, it will be totally fine. Like, okay, it takes 3 hours, but it doesn't matter. It's just 3 hours to design the network of a city. It's fine. But for my case, I need it to be as fast as possible. And so probably in the middle, I will be doing some approximations, or I will be getting rid of some variables I don't need just to make the problem faster, because I need it to be fast. And if I just plug this into a solver, maybe it's not as fast as I need it because the solver doesn't know what I need and what I don't need and so on. So, but the second option, as I say, will be just to use a solver. And then the third, of course, third options that I also considered and I started implementing too, is to use some generic meta-heuristic, which is like you can use a genetic algorithm or simulated annealing that should work for any kind of problem, not good enough, or not good enough, I mean, not as exceptionally well many times, but in many cases, they do work good enough. So they give you something and maybe they are sufficiently fast. So this is a valid approach, I would say. If you don't, if this, for example, if you plug it into an off-the-shelf solver and it's not good enough, maybe a meta-heuristic will be good enough and fast enough. Why not? But of course, this is like not, again, dealing with the details of the problem. So then what you can try to do, and this is something, and this is maybe one thing also to remember, almost always you can approximate your problem in such a way that you can formulate it as an MILP. This is actually very nice. So in some cases, so of course you should look into the literature and try to find if someone has already solved your very problem. And in many cases, you can find some tricks to transform your problem into a linear formulation, which is actually very good. And some other cases, there is no direct way of doing it. For example, in this case, I have not seen an exact reformulation of this problem into a linear problem, But one thing you can always do is try to approximate your non-linear function by something that behaves a little better. So in this case, what is making our problem non-linear, of course, there are many things, because you have this logarithm, this other logarithm, and then this rational function. But the first thing I will have to deal with is this double logarithm, which is, of course, non-linear. So one thing you can try to do is try to approximate it with, for example, a polynomial, because there is a nice feature that it should be also known, and is that if you have a polynomial expression in your integer problem, you can always transform it into a linear formulation. This is very nice. So actually, if you have a polynomial expression, so you can have like variables that are multiplying together and that are squared and so on, you can always transform your integer variables into 0-1 variables. And this is just like, so there are some techniques about this. Maybe I will also put it in the knowledge base, but it is very simple. So if I have, for example, one variable going from 0 to 3, as in this case, I can just express this as a function of two binary variables. So I just say x1 plus 2 times x2. And then this, each one goes from 0 to 1. So I can transform every integer problem into a 0-1 problem. And once it's transformed into a 0-1 problem, if it's a polynomial, you can always, and there are techniques to do this, there are also, you can always transform it into a linear formulation. Maybe I can also show like some, and there is a whole field on how to do this properly. So for example, like the first reference I could find about this was this paper. I think you can see it, right?
Yep.
And this is like the simplest rule that you can use to transform your polynomial problem into a linear problem. You just replace, since there are just 0-1 variables that you transform from your integer variables, you can just replace each each power of each variable by its single variable, because it will be just 0 to the power of whatever or 1 to the power of whatever, so it will be just the same variable. And then you can replace each cross product by a new variable and then add some constraints. And of course, this is like the simplest way of doing it. And then there are like many ways of improving it. So basically that reduce the number of constraints, as in this case. So, and also reduce the number of variables, because the problem with this is that, so you can always linearize your problem, and this is guaranteed, but maybe at the cost of a huge number of variables and constraints. So for example, if you have just a quadratic formulation of your problem and you have cross products between each two variables, the number of variables you need will grow with the square of the number of variables you have originally, because you have to have each cross product. So it's like, in this case will be, I think, I have it here like, exactly. So G times G minus 1. So this is G chooses 2, because you have like this number of pairs. So it grows with the square of the number of variables that you have. So this is one very important thing to realize. So in my case, I was able to linearize the problem, but I end up with such a large amount of variables and constraints that it is barely better than brute force. It's a bit better. But yeah, I mean, it still doesn't work very well with large problems. So this is actually a good thing to take into account. Like, you can always linearize your problem, but if you do it in a naive way, just systematic, like a solver out of the box, like a software solver could do it, you might end up with something that is really inefficient. It is linear, and you can use ILP and MILP solvers to tackle it, but it will be too large. So for example, in my case, I can show you an example. So originally, I have 9 base stations, so 9 original variables controlling the functional split of each of each base station. And then, so this will be like solving by brute force. I hope it doesn't crash because it actually takes some time. Okay, let's stop it.
But then basically for 9 base stations, you have 4 different variables. You have to try 36 values. Is that the case?
Yes.
Okay.
Exactly. So if I want to do it brute force, yes.
Yeah.
But somehow I can say originally I start with 9 variables. And for this linearized formulation, actually I will end up with 2,385. I know you can see it.
Yeah, we can.
2,385 variables. So out of 9, just with a simple linearization, like no tricks involved, I end up with over 2,000 variables. And you can see, and this scales actually with the square of this. So if I say
You
now
go
this
to
is
10, yeah.
exactly, if I say now this is 18, so I multiply this by 4.
Then you get to 10,000 level or
Exactly.
something like
So it actually is pretty nasty. I can do it. I can say my problem is now a linear MILP, and I can use the MATLAB to solve the MILP, but it's really, really large. And
I
actually,
wonder
another thing.
how sorry.
Yep.
I
No, please,
was
please.
wondering how would the runtime is comparing. So is it a problem to have too many variables? Because maybe MATLAB is good with vector operations and he doesn't care. You just have to use a huge memory, but if your memory writing, reading speed is okay, and then...
Yes, I mean, it's not as fast as I would like it, but it does the job. So since it's an MILP, this has been somehow already done efficiently. So there are some efficient implementations to solve it. And it's better, way better than brute force, but still is nothing magical. So, and exactly, and you need a lot of memory very quickly. And again, there are some techniques to reduce, especially the number of constraints and the number of variables. And you should be aware of this. So if you do a naive implementation, it's basically, so it's probably not helpful enough. And then one other thing, maybe the last one I want to mention, I just mentioned before that you can always approximate your function with a polynomial. And of course, this is true, but you also be very careful trying to approximate. Again, I'm no expert here. I just noticed with this. If you try to approximate your function with a polynomial, you might think this can be always done. You can do this Taylor series or maybe just polynomial fit and so on. But in some functions, they don't work really well. So in my case, I can show you even what it will look like. So if I want to do a polynomial adjustment of the logarithm of the binary logarithm, which will look like something nice to do, I will end up with something like this. Can you see it?
Yeah.
Yes.
So if I want to, for example, if I just say, okay, I will approximate it with a linear function, actually this doesn't work too bad, let's say. It's of course pretty bad. So in this, what you can see is like the polynomial adjustment of this blue function between 0.1 and 100. So this is the range I consider to be most likely for my values. And I wanted to see how this then scales up to 200. So this will be like 20 dBs and 23 dBs. Because this is NIR, SNIR. And you can see that, of course, the linear adjustment is not very good. Actually, it just forgets about the data rate or the Shannon's law. It just says, okay, this is basically interference and it scales linearly with interference. But it's actually not too bad, I will say, because if you look at the other options, you might think that, okay, a second degree polynomial probably works better, right, than a first degree polynomial. But the thing about this is that if you try to do this, you can see that, of course, you get a parabola, which is behaves very, very differently to the original function you wanted. And this is what I also could observe. So you can see that it is more or less well fitted, actually not very good, but it's more or less well fitted between 0 and 100. But if you get like 140 instead of the values you originally planned, your function actually decreases quite steeply instead of increasing as your function should do. And if you go for a third degree, the opposite happens. Your function increases, so the fit at this point is very good, but then your function increases very steeply, so far faster than your original function does. And if you go for a fourth degree, from between 0.1 and 100, the fit is really good, but then it decreases, so it basically plummets to minus 40, minus 60 when you go from 20 dBs to 23 dBs. So this is also one thing that might be helpful for you if you're dealing with this kind of optimization of logarithm functions. Actually, polynomial adjustment is not good at all. And I would recommend, and this is what I have been doing, this rational adjustment. So for this, you can use, as I mentioned some weeks ago, these Padé approximants, which are the equivalent of Taylor series of rationals. Or you can use just rational fitting in MATLAB. This also works. And you can see, for example, this now, the blue is the original function, and then the red one is the degree 1 approximation, and the yellow one, I hope you can see it, is degree 2 approximation. And of course, you can see it's not perfect, especially the first one, so the first degree, but at least you can say this behaves in the same way as logarithm. Mm-hmm. So it grows a bit less than the logarithm, especially the first degree. The second degree is actually quite good. It fits quite well, the logarithm. But at least it doesn't do any crazy things like polynomial adjustment. So if you deal with some kind of these problems, you can learn from my experience that maybe polynomial adjustment is not a good idea at all, because it might yield totally crazy values if you exceed your range that you planned. But if you have some kind of function like this, you can use some rational approximation. And this is actually a bit worse, because then you are dealing with rational programming. So this is like you can see here, I approximate the logarithm either by one function or one rational function or two rational functions. And this is actually a much better fit than polynomial. And still it's somehow a large field in optimization. So you can find a lot of literature on fractional optimizations, and in many cases, you can find good algorithms to deal with fractional optimization that in the end also transform it or linearize it to an ILP or MILP.